Hello, welcome to this video. In the last video, we saw that few numbers cannot be represented with a finite binary representation. This can lead to bugs in our code. We took an example of 0.1 plus 0.1 plus 0.1 is equal to 0.3. This is a mouthful, isn't it? Now, let us set a fixed precision of 0.1 to 25 and see what the result is. I'm console logging it. Console log 0.1 to fixed. I'm using the toFixed method by JavaScript. That's an inbuilt JavaScript method. And I'm setting the fixed precision to be 25. And when I console log it, we get 0.1 with so many zeros and with 555, 1151. There are so many leading zeros and only near the 17th decimal point we get a change. That is 5 in the 17th decimal point and so on. Now instead of me logging out for each individual 0.1, I'm going to multiply it with 3 and see what the result is. We get 0.3 with so many zeros and 4 at the end. Now let us console log the fixed precision of 0.3 and set it to 25. We can see that the result is 0.2 and so many 9s, so many 8s, 9, 7, 7, 6, 9, 8. It clearly is not equal. So this is the sole reason why 0.1 plus 0.1 plus 0.1 is not equal to 0.3. And that is why we fail when we do the comparison testing, when we use triple equals to or double equals to. Now you might be thinking that what if we set individual precision, that is toFixed method, to each individual value and compare it. This is going to fail because we are simply applying it to each value, which is not going to have any effect. But it can be used to the entirety of both sides, and when we do that, we get the output to be true when we do the comparison testing. And let me show you what I'm talking about. Console.log 0.1 plus 0.1 plus 0.1, and I'm setting the toFixed value to be 5 this time, and let me do the comparison testing with 0.3, and I'm setting the precision to be 5 for 0.3 as well. And when let me clear the console, and when I'm commenting the first 3 lines. Okay, and when I execute this code, we get the output to be true. But this is not flexible. Here we saw the precision up to 5. What if you want to change 5 to 25? And when we run this code, we'll get the output to be false. To solve this problem, wait, and I'm clearing this. Okay, to solve this problem, we can use absolute tolerance as a fix. What is absolute tolerance? Absolute tolerance is a threshold below which the value of the ith solution component is unimportant. Let me break down the definition for you. We use an appropriate range, let's say epsilon, and I'm denoting epsilon with E. Epsilon, and epsilon is greater than 0 for A equals to B, that is A variable as 0.1 plus 0.1 plus 0.1 and B is 0.3, and for both of them to equal, it should match the condition where absolute value of A minus B is less than epsilon. Only when this condition satisfies, we'll get the output to be true. I'm clearing them. Okay. Let me tell you what I'm talking about. Let us code a function and let our epsilon be 10 to the power minus 15. That is, our absolute tolerance is 10 to the power minus 15. I'm writing the function, and I am writing an anonymous function, and I'm assigning it to is equal variable, and the anonymous function has 3 parameters, A, B, and epsilon. And I'm returning math.absolute value. Absolute value is an inbuilt method inside of JavaScript. I forgot to put arrow here. Okay, absolute, and I'm passing A minus B and checking if it's less than epsilon. Cool. Now let us assign the variable A, where A to be 0.1 plus 0.1 plus 0.1, and I'm assigning variable B the value 0.3, and I'm assigning tolerance to be 10e to the power minus 15. Now let us run the function. Console.log is equal, and I'm passing the arguments A, B, tol. Let us see what the value is this time. We get the output to be true. But there is a problem with this solution. Our absolute tolerance was 10 to the power minus 15, and it was for 0.1 plus 0.1 plus 0.1, and the value was 0.3. But if we change the 0.1 to be 1 lakh point 1 plus 1 lakh point 1 plus 1 lakh point 1 and b to 3 lakhs point 3, we'll get the output to be false. I'll show you why after this example. I'm setting it to be 1 lakh point 1. I hope I'm getting the zeros right. 3 lakh. Let us check now what the value is this time. See, we got it as false. I'll tell you why we get false when I change the value from 0.1 to 1 lakh point 1. Let me, I'm commenting these lines. Let me write down the code and I'll show you what is happening. Console.log 0.1, 0.1 plus 0.1 plus 0.1 to fixed 25 minus 0.3 to fixed 25. Okay. And I'm fixing 25 to the entirety of the solution. Now when I run this, let me bring this a bit up. Okay. When I run this, we get the output to be 0.000, and near the 17th decimal we have 5. Remember that near the 17th decimal we have 5. This is when we subtract a minus b. Now let us console log the value of epsilon and see what's happening. Console log 10e minus 15, and we are setting it to this precision up to 15 because our tolerance was 15 in our example. Okay, we can see that epsilon is 0, 0, 0 and 1. We can clearly see that a minus b is much smaller than epsilon, and our equation, that is this expression, satisfied, and we got the result to be true. Now for what happened with 1 lakh is, let us see. Let me copy paste and I'll change the values. It's going to save us time. Okay, 1 lakh, 1 lakh, 1 lakh, and I'm setting it to be 25, and here I'm going to put 3 lakhs in place of 0.3, and I'm setting the fixed precision to 25. Let me console log this for you, and we have the value 1, 2, 4, 6, 8, 10, 5, 8. Okay, and you can see that this a minus b is smaller than epsilon. Sorry, it's greater than epsilon, and it's not satisfying our condition, and this condition fails and we are getting the output to be false. See, this is the problem in our solution. Now we are setting the tolerance to be absolute value. We are fixing it. So this solution is not the perfect solution for us. Let us try the next approach, that is relative tolerance, in the next video. Thanks for watching this video. See you in the next video.